for the any questions about this? No? Okay, good. So this should be very straightforward. So now I'm going to talk about the individual orbits. The first one is elliptic orbit. Okay, the first one is the size of orbits here. So here, this is the orbit. So this is the occupied focus. This is the vacant focus here. So this is okay. So here we give our symbols being used here. So 2a is the major axis, and c is the distance between the foci, and from here on the top, this is the 2b, the minor axis. Okay, and again, this is our perigee, and here we define the distance. Here is rp, and we've been using it earlier, and this is apogee. So the distance between here is probably RA. So those are the symbols we use. And for this case, we can have is P, the parameters, or for the, I forgot that term. Anyhow, it's not, it's okay. So for this one, P, equal to this, and also h being calculated can be expressed in terms of the information at either perigee or apogee. So if you wish, you can say plug in here. So basically that is VA RA and divided by mu squared. Or if you wish, you can also write it up as the VP RP squared. Okay, and that is the speed here is VP, and speed here is the VA. Okay. And also, the value of the A can be related to the mechanical energy equal to minus mu divided by 2E. Okay, so here the A is the geometric information about these conic sections, and E is the mechanical energy. So right now you can see in these sections I try to relate the orbit information like the energy or parameter to the conic section information here. Okay, and also from the tables, and we have is C equal to A times E, and B equal to A 1 minus E squared. So that is P times 1 E, etc. Okay, so RP we can also describe as P 1 plus E, and RA equal to P 1 minus E. And etc. Okay, so that depends on the information you would need from when solving a problem. So many things can be derived from each other. So here is only one example here. And this is about the size of the orbit. The second one I want to talk about is the period. So this will be the first time we involve time. So continue. Okay. This is the period of an elliptic orbit. So if you remember from Kepler's law, we already have is this. So this is the orbit, and this is the the occupied focus. Okay, so here this is the object moving from here to here. So it's moving, and here is taken. This is theta. Sorry. So this is the area being swept by the motion of the satellites in the orbit. Okay. So this area we can earlier we seen this is the 1/2 times r times r d theta. So basically this is the r, okay, radius. So here this is r d theta at the infinitesimal movement. So therefore here earlier we seen dA dt can be written by 1/2 r squared theta dot. And this one actually earlier we seen is half of the momentum. Okay. So, which means the sweeping the area by a constant speed, h/2. So we consider an elliptic orbit. So this one has the with the semi-majors axis A and minus B. Okay. So for this elliptic ellipse, its area equal to pi AB. Okay, so that is information we have from conic sections. And so therefore you can see if this is a focus here, and at any given constant time, it's sweeping dA dt equal to h/2. So that means once we sweep the whole entire area, how much time we would need. And that is defined as the period of the orbit. Okay? So once we swap, so from here to here, so at any given constant period of time, it will swap with the same, the area speed. So therefore, the period that defined as the sweeping the whole area by this constant speed and h/2. So that is 2 pi AB divided by h. And this is the basic formulas, and we can derive more quantities here. So with these equations, we can with the placement is say h equal to with the information is because we know that P is defined by h squared over mu, and so therefore we can replace h squared by h by p mu squared. Okay, and what is p? P here I'm going to use other informations, and here I don't have. Probably I can add it up. P can be also described as the a 1 minus e squared. Okay, using this one. So here that is mu. Okay. So with this information, the second one, we can utilize this information. We can relate, try to cancel everything. So B equal to A times 1 minus E squared. That pretty much, yes. Okay. So with the two information, we can replace B and H in terms of A and E. So we see what happens. So therefore, T will become 2 pi A squared minus E squared. So that one can be rearranged is 2 pi over mu. Sorry. So this is the useful information for calculating period. So from here, you can see the period can be only determined by one parameter of the conic section A. Okay, so which means if we have two different ellipses, one has the smaller a, one has the larger a. So from there, the larger a corresponding will be the larger period. Okay. So from here we have we can have the one derived quantities. So from here you can see because t squared, by deriving this one, t squared equal to 4 pi squared divided by mu times a3, a cubed. So therefore, in this way we have is the t squared divided by a cubed equal to constant. So this one is, in my notes, I think this is people refer to as calculus third law. Okay, so that one, if you wish, I can make a few examples here. So this one is true for all the planets, for all the celestial objects in the universe. As long as they can be described, approximated by two-body the province. Okay, so okay, so I think the textbook have this as an example here. So maybe I can try is this.